Antarctica, I am discovering, is a land of flags. The flags are quite small, they're pennants really, I suppose, mounted on a tall bamboo pole, and they mark the routes where you can and can't walk. And they're a really good barometer of the wind. So here we have a flag. And when I left Scott Base about 10 minutes ago, it said it was about 6 knots. So quite a light wind down here. I'll keep an eye on the flag barometer through the rest of the podcast. Kia ora, I'm Alison Balance from RNZ, and this is Voices from Antarctica. In part 3, From Flags to Physics, I'm continuing my exploration of what it's like to live in and do science in Antarctica. I'm going to open the outside door and see what it's like outside. And it's mildly windy and pretty friggin' cold, about minus 19, I think. Let's just go back inside. I spent the first week of my trip waiting to get to the ice, and then my helicopter trip yesterday was cancelled until today due to the weather. I'm at New Zealand's Scott Base, and I'm packed and ready to go, and so is my field trainer and safety person, Scott Barry. What's the story, Scott?
We are still on standby, waiting for a good weather clearance. Looking at sort of an hourly update from the crew already out at Cape Crozier, and hopefully within the next couple of hours we'll see a good clearance and we can head on in.
I see blue skies and sunshine outside. That's pretty exciting.
Yeah, absolutely. It's starting to break out above us, and hopefully in the next sort of hour or two we'll see the same thing occurring out towards Cape Crozier.
In the meantime, we're going to have
standby.
Since I'm waiting, I've got time to talk to someone whose job is dealing with these sorts of delays. And although I've got my own wind barometer, the flags, I can also find out about Antarctica's more formal weather rating.
My name is Shul Gordon, and I'm the operations scheduler at Scott Base.
What does that job involve?
It mostly means that I schedule the helicopters and small planes that move in and out of Scott Base, but also people, whether they're going on Haglins or planes from here to New Zealand, and meetings that we've got to have with the groups when they arrive at Scott Base and then when they leave Scott Base. So just general scheduling.
And these are schedules that change all the time, and I know that from personal experience.
Yeah.
So you then have to juggle everything that's changed as a result of that.
Yeah, pretty much. The plan that we set over the winter, we know is a baseline kind of a plan, and that it's going to change. And so every day that a plane doesn't come down, we change our plans to the next day and the next day and the next. So there's a lot of juggling that goes on and a lot of rescheduling.
Now, one of the things I haven't covered off down here are the weather conditions. So can you quickly run me through the 3-point weather scale?
Normal conditions is condition 3.
Which is what we have at the moment.
Which is what we have at the moment, where you've got good visibility, decent temperature, winds aren't too high. You can basically move around, no problem, without any danger to yourself. Where the condition 2 comes in, so it could either be that the temperature reduces, the wind increases, or the visibility reduces, which means there'll be some restrictions on the way you travel around out of base. And so with that, it just means that you have to get permission to travel off of base. And then condition 1 is that really either one or all 3 of those are really quite severe, and all movement off of base is restricted, full stop. Sometimes it can just be really cold, but mostly it's because of visibility. You actually can't see around you, and with that comes the fact that there's a high wind speed.
You've experienced a few condition 1s?
A few. Actually, we came down relatively early this season in mid-September, and there was a couple of doozies that were quite exciting. In fact, one time I was just about to go to bed and the whole building just creaked and shook in a way I haven't felt it before. And everybody came out of their rooms. In fact, we came out to the front here, and you could barely see the front of the banister there, and the wind was just pounding against the window. And the strong winds are from the south. The base does face to the south, so it really does get hit. It was quite exciting and a little bit unnerving, but recognising this building's been through many condition 1s, and so figured we're pretty safe.
Here's something I recorded earlier. at Scott Base back in 2010. The wind was at 30 knots and rising towards a condition 2. I was sheltering behind a building, trying to keep the wind off my microphones. Weather like this really makes you appreciate more than ever the warmth of Scott Base when you get back inside.
My name's Adam Craggs. I'm the power engineer at Scott Base. I look after the heating and ventilation as well as the diesel generators.
So it's a nice temperature here. What temperature do you keep Scott Base at?
Inside it's usually somewhere between 18 and 20 degrees Celsius.
So the things that you look after are what?
The diesel generators, it's quite the easiest one to picture, but we've also got air handling units which basically heat and filter the air around the base, keep it nice and warm and clean, as well as the fuel for all of those things as well.
To run something like that in a temperature like we've got here in Antarctica, do you have to do something special with the fuel?
It's basically almost an aviation grade fuel, which it's pretty much very clean diesel with a ice inhibitor to stop it from freezing, which basically anything that runs on diesel, like all our heavy plant, like bulldozers, even the Toyotas, the Haglunds and the diesel generators all use the same thing. So it's quite handy.
So is it complicated looking after machinery like that in a remote place like Antarctica?
Basically, spares are always a factor. You've got to wait until a plane comes down. If you find a plane's been delayed, then that piece of equipment's not going to get fixed until the plane gets there. And then it's got to be the right part. Sometimes it arrives as not the right part. So yeah, there's always that.
Luke Kean helps keep the lights on and the power running.
Scott Base is electrically linked to McMurdo Station, the American station, and in between the system we also have a wind farm which helps supply energy. So our two systems are fairly closely aligned. There is a mixture of 3 big diesel generators at Scott Base, of which any one of them is more than capable of covering Scott Base's energy requirements. We have 3 big turbines up on the hill.
They've been there a few years now, haven't they?
They have been, about 10. I think they were commissioned about '09, somewhere around there. And then McMurdo have 5 very large generators that they use, but of which they realistically only need a maximum of 2 going at any one time to support their base. And the electricity system is smart enough to be able to look at how much wind energy is being produced through the wind farm and sort out where the most efficient way of drawing energy to power both stations comes from, and it can turn on and off generators of differing sizes as it needs to maximise that efficiency.
So on a day like today, there's a little bit of wind out there, but it's not extremely windy. How much power are those turbines generating? Can you tell by looking at that screen?
I can. So what we're looking at is each of the turbines is producing nearly full power. A little bit under full power at the moment, so we're looking at 330-ish kilowatts per turbine. Given that the total load for the island is about 2 megawatts, we're producing 45% roughly via wind energy at the moment, which is pretty good.
So more than enough for Scott Base.
Oh, well, more than
quite
enough.
a lot of McMurdo's power as well.
Yeah, so it's very advantageous for us to be able to supply them with electricity. It means that they can take one of their big generators offline completely, run on one generator. That saves them a lot of fuel cost. And that is part of New Zealand's contribution to the joint logistics pool. It's a really good way of us being able to help reduce the entire island's carbon footprint. Every now and then you run into a few issues, as things do, and at the moment we're just progressively working our way through one that happened yesterday from a power outage, but we're expecting that by tomorrow morning we'll be back in full island production. It happens every now and then. It's part of being in a place like this. It's part of any generation system.
So what does all of that power get used for? I mean, the lights and computers, obviously.
Yep. There is a lot of energy goes into water production. Water production's a very energy intensive exercise. Our reverse osmosis plant uses a fair bit of water. The Americans have 3 plants that they run, which are very large. That produces a lot. There is cooking and heating and all the normal things that you use electricity for anywhere else in the world, we do the same here.
How are those flags getting on? Moderately light winds at the moment. Right, I'm going to segue from flags to physics, because I've got permission to visit a scientist working in a very special area on Ross Island, partway between Scott Base and McMurdo Station.
I'm James Brundell. I'm from the physics department at the University of Otago, and I'm a research fellow there in the space physics group.
We should perhaps explain where we are now, because it's quite a noisy room,
Yes.
but it's a really special place.
It is a very special place. We're here in New Zealand's science lab in Arrival Heights. We're inside a ASPA, the Antarctic Specially Protected Area, and the one we're in is ASPA 122, which is a designated radio quiet zone. We're here using Antarctica as a vantage point. So we come here with our radio receivers because this is a good place to receive radio waves that have travelled through an interesting part of the world, where energy from the sun and from outer space will come in, hit the Earth's magnetic field, and that energy can get channeled down into the polar regions. So we pick up radio waves in a frequency range called the very low frequency, where the wavelength is many kilometres long. And waves at that frequency can travel a long way because they reflect off the very lowest layers of the ionosphere. And if that energy coming in from space, maybe some charged particles, maybe some high-speed electrons, energetic particles of some sort, they'll come down and they'll hit the upper atmosphere, hit into the ionosphere, and create a disturbance in that ionosphere. And then our radio wave coming to us from Australia will get disturbed by that disturbance in the ionosphere, and then it'll carry on to us down here in Antarctica, and we'll see a change in that signal. So we pick up signals from Australia and Hawaii, and even from North America and Japan and India, all across the world.
The signals come from large aerials that communicate with submarines. I've seen the Australian aerials. They're part of a naval communication centre at Exmouth in northwest Australia, and they are very tall. 387 metres is the tallest. In Hawaii, there's a VLF aerial that's 458 metres high. By comparison, the tallest aerials in New Zealand now are the 153 metre high RNZ radio transmitters at Henderson and Paengaroa. But I digress. Back to Arrival Heights and to James, who is very excited that I've seen one of the sources of his signals.
Wow, I've never seen it myself, so that's really cool. What was it like?
It was just a lot of aerials with a fence around it.
You can see it if you zoom in on Google Earth in that region. You can look down and you can see it from outer space. It's like so massive, yeah.
Right, so you're just eavesdropping on...
Yes, that's a good way of saying it. Yeah, eavesdropping on those signals. And they'll propagate out for thousands and thousands of kilometres, and they're very stable too, so the signal is a very steady tone. And so we carefully measure that stability and any small change in the signal, which we're quite sensitive at picking up.
The signals leave Australia, they bounce off bits of the atmosphere.
Bits of the ionosphere.
The ionosphere. So quickly talk me through from Earth going up, whereabouts does the ionosphere fit in?
So we're down here at a few hundred metres above sea level. As you travel up, say up 10 kilometres, that's like where you might, if you're flying international flight, you'll be at about 10 kilometres. You carry on further up in the daytime, the ionosphere, meaning where the atmosphere starts to become ionised, ionosphere, that starts to happen around 70 kilometres and maybe 70 to 90 kilometres depending on the time of day. And then further up there become more and more enhanced layers of the ionosphere.
And we talked about aerials at Exmouth. You have an aerial here as well?
Yes. Luckily it's very easy to receive these signals. We have a small antenna about 4 metres high, and we pick up the magnetic field component of the radio waves.
So there's a bit of aerial maintenance to be done, given that Antarctica is quite a harsh environment for
Yes,
things
so
outside.
our experiment here runs all year round, right through the Antarctic winter. Sometimes the science techs will take a photo of the antenna for us from the middle of winter, and it looks like it's been stuck in a blast freezer and someone set a hose on it, and it's just covered in an icy mess. But it keeps on running. We keep getting the data every night. We stream the data back.
One of the things James and his colleagues measure with their radar is activity on the sun.
A student in our group looked at data over the last 10 years on the signal from the Hawaii station, looking for particular events we call solar flares. And solar flares are when there's a big blast of X-rays come out of the sun. So these solar flares, the X-class events, come in, and we can see that on our data received here. We see the phase of the signal starts to rapidly change when this X-ray hits. And by analysing these flares, we could see the onset of these flares maybe a minute or two before some of the even satellite data could detect that these X-rays are coming in. And of course, early detection of these events is of interest to many people. The international aviation community are very interested in monitoring for space weather, and there's an upcoming requirement that aircraft start to take into account the possible influences on space weather.
Whew. I think that's enough of that noisy room. Let's head back to Scott Base.
Now, there are a lot of corridors at Scott Base, and I will not subject you to all of them. Suffice to say, it takes many minutes to walk from one end of Scott Base to the other, because it's a whole lot of separate buildings, and they're joined by fireproof corridors with the idea that if there's a fire, it's not going to spread all through one building, but you can isolate different buildings. Lots of walking. I haven't even left the Hillary Field Centre yet, and that's only one building. Oh, here we are in another building.
James, hello. I have tracked you down,
Yes, you've found me up here in the Heatherton lab at Scott Base.
which is the furthest corner of Scott Base.
Yes.
And this is where you have the lightning detector.
This is right, yes, we've got another VLF radio receiver.
So VLF, very low frequency.
Again, it's a VLF. Our antenna is a very low frequency antenna, because that's where a lot of the radio energy from lightning comes from. So you might have been in your car maybe, and it's in the summer, and there's been a nearby thunderstorm, and you might hear crackles on the car radio, and it's the same principle down here, but we're at lower frequencies. Those radio waves travel even further. They can travel right around the world, and our receiver here at Scott Base is part of a network of about 80 of these receivers around the world, and each receiver detects that little crackle of lightning and precisely times it down to about a millionth of a second. We then send that data over the internet back to our central processing computers in New Zealand, and another one in the US, and where we have software that collates all those arrival times of the lightning flashes and works out sort of by a triangulation process where the lightning actually happens in the world.
So where is the lightning currently happening? You've got a map on the computer screen?
Yes, there's a map there, and at the moment we've got a lot of lightning in South America, through Africa, and up through Asia, Singapore, and there's a wee bit just starting up in Australia.
What I am not seeing is any lightning in Antarctica.
That's right. You won't see lightning in Antarctica. Too cold and too dry. And lightning likes the exact opposite. It likes lots of heat, lots of energy, and lots of moisture to generate the physics of it.
Now, are we able to listen to the lightning?
We can. Our very low frequency waves are actually radio waves at the same frequency as humans can hear it, so we can turn it into like a pseudo sound, if you like. Actually,
Mostly what you can hear there is interference from another radar system, apparently. The lightning is the very high, crackly bacon sounds on top of the loud buzz. Who knew? Round the world there are about 45 lightning strikes per second, just not in Antarctica. And that's it for this episode of Voices from Antarctica, a podcast series from RNZ. I'm Alison Ballance. A big thanks to Antarctica New Zealand and the staff at Scott Base for hosting me and my microphones. Next time I will hopefully make it to Cape Crozier. You can find Voices from Antarctica at rnz.co.nz/Our Changing World or at RNZ Our Changing World wherever you listen to podcasts. Catch you next time. Kia ora mai.